Most of us grow up believing that the solar system is simply a collection of planets orbiting the Sun. Beyond Neptune, beyond Pluto, there is only more empty space. Continue travelling long enough, and eventually you leave the Sun behind. It seems like a journey defined by patience rather than difficulty, as though the edge of our cosmic neighbourhood is little more than an invisible line waiting to be crossed. Modern astronomy paints a quieter and far more intriguing picture. The solar system is not merely a family of planets scattered through space. It is surrounded by an immense, flowing bubble carved out by the Sun itself. Invisible streams of charged particles race outward in every direction, carrying the Sun's magnetic influence billions of kilometers into the darkness. Long before a spacecraft reaches another star, it must first navigate this enormous and constantly changing frontier. Yet even that frontier is not the true obstacle. The greatest challenge is not finding the edge, it is understanding what lies beyond it. The space between the stars is often described as empty, but it is filled with magnetic fields, drifting atoms, energetic particles, and distances so immense that familiar ideas of travel begin to lose their meaning. The farther we look, the less the universe resembles the maps we once imagined. Humanity has already sent a few small machines toward that distant horizon. They continue their silent voyage, carrying faint whispers of our civilization into a region no human being has ever visited. Their discoveries have shown that the boundary between home and the wider galaxy is neither sharp nor simple. If the edge of the solar system is not a wall, but a gradual transformation stretching across billions of kilometers, then what does it truly mean to say that we have finally left home for thousands of years? The solar system appeared beautifully simple. The sun rose and set with dependable rhythm. The planets wandered slowly across the night sky. Comets arrived unexpectedly, lingered for a season, and disappeared again into the darkness. Even after the invention of the telescope transformed astronomy, the picture remained comfortably familiar. The solar system was understood as a collection of worlds bound together by gravity, each following predictable paths around a single ordinary star. That picture remains fundamentally correct. The Sun contains almost all of the solar system's mass. More than 99.8% of everything that formed from the ancient cloud of gas and dust over 4.5 billion years ago became part of the star at its center. The remaining fraction condensed into planets, moons, asteroids, comets, dwarf planets, and countless smaller fragments. Every object, from Mercury's scorched surface to Neptune's frozen atmosphere, follows the Sun's gravitational pull. From a human perspective, this family already feels unimaginably large. Light, travelling at nearly 300,000 kilometers every second, needs a little more than 8 minutes to reach Earth from the Sun. That same beam of light requires over 4 hours to reach Neptune, the outermost major planet. A spacecraft launched today, even using the most powerful rockets ever built, would spend years crossing distances that sunlight covers in only a few hours. And yet, the planets occupy only a tiny fraction of the Sun's true domain. Beyond Neptune lies a region once thought to be almost empty. Instead, astronomers have discovered a vast population of icy bodies. Pluto, once regarded as the 9th planet, is only one member of this distant family known as the Kuiper Belt. Thousands of frozen worlds orbit here, remnants of the solar system's earliest days. Some are only a few kilometers across, others rival Pluto itself in size. These objects preserve something remarkable, unlike Earth, whose geology has continually reshaped its surface. Many Kuiper Belt objects have remained largely unchanged since the solar system formed. They are deep freeze archives, preserving ancient mixtures of water ice, methane, ammonia, and more complex organic compounds. By studying them, scientists gain a glimpse into conditions that existed billions of years before life appeared on our own planet. But even the Kuiper Belt is not the end. Far beyond it lies a region that no telescope has ever directly photographed in detail, the Oort cloud. Proposed through careful analysis of long-period comets, may surround the solar system like an enormous spherical shell, If it exists as current models suggest, it stretches perhaps 50,000 astronomical units from the Sun, and possibly much farther. An astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. At 50,000 AU, sunlight becomes astonishingly weak. The familiar warmth that shapes life on Earth has faded into little more than another bright star in the sky. A spacecraft travelling at the speed of Voyager 1 would require many thousands of years to pass through this distant reservoir of icy objects. This immediately changes our sense of scale when we picture the solar system. We often imagine the orbits of the planets. In reality, those colourful diagrams barely represent its inner rooms. If the orbit of Neptune marked the edge of a small coin, the Oort cloud would extend outward over distances so vast that the entire planetary system would almost disappear by comparison. Gravity is responsible for holding all of this together, but gravity itself never truly ends. Every object with mass exerts a gravitational influence across infinite distance. The Sun's pull gradually weakens, yet mathematically it never reaches zero. This creates an interesting question. If the Sun's gravity extends forever, then where does the solar system actually stop? Astronomers answer that question in several different ways, depending on what they are measuring. One definition concerns gravity. Another concerns the flow of charged particles emitted by the Sun. Another concerns the regions where comets remain loosely bound over billions of years. None of these boundaries lie in exactly the same place. The solar system has no single fence surrounding it. Instead, it possesses several overlapping frontiers, each revealing a different aspect of the Sun's influence. Perhaps the most fascinating of these frontiers has nothing to do with planets at all. The Sun is constantly shedding part of itself. Every second, millions of tons of charged particles stream away from its outer atmosphere. This continuous outflow, called the solar wind, races outward at hundreds of kilometers per second. It carries magnetic fields with it, filling space with an invisible current that stretches far beyond Pluto. Earth exists entirely inside this flowing river. Our planet's magnetic field protects us from much of the solar wind, producing the shimmering auroras that dance above the polar skies. Every planet interacts with this stream differently. Mercury faces it almost directly. Jupiter's immense magnetic field reshapes it. Saturn, Uranus, and Neptune carve their own disturbances into its flow. For centuries, no one realized that this invisible wind even existed. It could not be seen through telescopes. It left no obvious trail across the night sky. Only during the 20th century, through advances in plasma physics and the first spacecraft venturing beyond Earth's atmosphere, did scientists recognize that the Sun is not quietly shining into empty space. It is continuously breathing outward, surrounding the planets with an enormous magnetic environment. That discovery transformed our understanding of the solar system. It also hinted that the Sun's influence might extend much farther than anyone had imagined. But another realization soon followed. Even this immense outward flow cannot continue forever. Somewhere, unimaginably far from Earth, the pressure of the solar wind must eventually meet the equally persistent pressure of the galaxy itself. Where those two invisible oceans collide, the familiar solar system begins to change into something altogether stranger. The farther we travel from the Sun, the quieter the solar system appears to become. The bright planets fade behind us one by one. The warmth of sunlight diminishes until it is scarcely more than a brilliant point against an ocean of black. The familiar architecture of our planetary neighbourhood slowly dissolves into scattered icy bodies and immense stretches of seemingly empty space. It is tempting to think that, beyond this point, nothing important happens until another star is reached. Nature rarely draws its boundaries so simply. The solar system does not end with a sharp edge. Instead, it gradually blends into the wider environment of the Milky Way. Somewhere in that transition, the Sun's influence weakens enough that it must contend with forces originating far beyond our own stellar neighbourhood. To understand why this matters, it helps to think of the Sun not only as a source of light and gravity, but also as a moving star. Although the planets orbit the Sun itself is far from stationary, together with its family of planets, asteroids, comets, and distant icy bodies. It circles the centre of the Milky Way at roughly 220 kilometers every second. Completing one galactic orbit takes about 230 million years, since the solar system formed around 4.6 billion years ago. It has completed only about 20 such revolutions. This means our entire solar system is constantly travelling through the thin gas, dust, magnetic fields, and energetic particles that fill the space between the stars. Astronomers call this environment the interstellar medium. The name may sound unremarkable, but the interstellar medium is one of the defining features of our galaxy. It's not a perfect vacuum. Every cubic centimetre typically contains only a handful of atoms, along with electrons, magnetic fields, and high-energy particles known as cosmic rays. Compared with Earth's atmosphere, it is unimaginably sparse, yet across the vastness of the galaxy, even this tenuous material becomes significant. As the Sun races through this environment, something remarkable happens. The solar wind continues expanding outward in every direction, carrying the Sun's magnetic field with it. At first, this outward flow easily overwhelms the surrounding interstellar medium, but distance steadily weakens the solar wind. As it spreads across an ever larger sphere, its pressure decreases, much like ripples becoming gentler as they expand across a pond. Eventually, another force begins to push back. The interstellar medium is not standing still. Relative to the Sun, it behaves almost like a gentle cosmic headwind. The outward pressure of the solar wind meets the inward pressure of the surrounding galaxy, and between them, a vast invisible boundary begins to form. This enormous structure is known as the heliosphere. It is not a solid shell, nor a perfectly round bubble. Instead, it is a dynamic region sculpted by competing pressures, magnetic fields, and the Sun's own activity. The heliosphere surrounds every planet and extends far beyond the orbit of Pluto, enclosing our planetary system inside a protective envelope created by the Sun itself. One way to picture it is as the bow wave formed around a ship moving through water. For many years, astronomers believed the heliosphere might resemble the long, comet-like tail behind a speeding boat. As observations improved and computer simulations became more sophisticated, the picture became less certain. Some studies suggest a shape resembling a rounded croissant, shaped by the Sun's magnetic field. Others indicate a more elongated form with extended lobes. The exact geometry remains an active area of research because it depends on complex interactions that are extraordinarily difficult to measure directly. What scientists agree upon is more important than the exact shape. The heliosphere acts as a vast shield, high-energy cosmic rays, produced by exploding stars and other energetic events across the galaxy, constantly stream through interstellar space. Many of these particles possess energies far beyond anything produced naturally on Earth. As they encounter the heliosphere, the Sun's magnetic field deflects and slows a significant fraction of them before they can penetrate the inner solar system. Earth owes part of its habitability to this invisible protection. Our planet's own magnetic field shields us from many charged particles arriving near Earth, but the heliosphere performs the first line of defense on a much larger scale. Without it, the inner solar system would experience a much greater intensity of galactic cosmic radiation. The strength of this shield is not constant. The Sun follows an approximately 11-year cycle of magnetic activity. During periods of high solar activity, the solar wind becomes more turbulent, and the heliosphere tends to block cosmic rays more effectively. During quieter phases, more galactic particles find pathways into the solar system. Even here on Earth, scientists can detect subtle changes in cosmic ray intensity that reflect this long rhythm of our parent star. Yet every shield has a limit. As the solar wind continues outward, it eventually slows from supersonic to subsonic speeds in a region called the termination shock. Beyond this lies the heliosheath, where the slowed solar wind becomes increasingly compressed and turbulent as it presses against the interstellar medium. The heliosheath is unlike any environment found near the planets. Particles become tangled within distorted magnetic fields. Plasma flows in unexpected directions. Conditions change over enormous distances. Computer models can describe many of its broad features, but only direct spacecraft measurements have revealed how surprisingly complex this region truly is. Farther still lies another boundary. This is the heliopause, often described as the outer edge of the heliosphere. It marks the region where the outward pressure of the solar wind is balanced by the pressure of interstellar space. Beyond the heliopause, the solar wind no longer dominates, instead. The environment belongs primarily to the galaxy itself. Even here, however, the story remains more subtle than a simple crossing. The heliopause is not a wall. It is not a sharp membrane like the surface of a planet. Charged particles, magnetic fields, and plasma continue interacting across it. Some particles cross inward, others escape outward. The boundary shifts over time as solar activity rises and falls, breathing gently with the changing rhythm of the sun. This means that leaving the heliosphere is not like stepping across a border between two countries. It is more like sailing out of the mouth of a great river into the open sea. Fresh water gradually mixes with salt water. The current changes direction. The familiar flow weakens while another begins to dominate. There is no single instant when every traveller would agree that the river has ended. Astronomers therefore distinguish carefully between different meanings of leaving the solar system. A spacecraft may leave the region dominated by the solar wind while remaining firmly bound by the sun's gravity. It may enter interstellar space while still taking tens of thousands of years to escape the distant Oort cloud. It may travel beyond one boundary only to discover that another lies much farther ahead. This layered picture overturns one of our simplest assumptions. The solar system is not surrounded by a single edge waiting patiently to be crossed. It is a collection of overlapping frontiers, each revealing a different relationship between our star and the galaxy beyond. For decades, these boundaries remained theoretical. Scientists could calculate where they might exist. They could build increasingly sophisticated models. They could compare observations made from within the heliosphere. But no human-made object had ever travelled far enough to find out whether those predictions were correct. Then, in the late 20th century, two remarkably small spacecraft continued a journey that would carry them farther than anyone had originally imagined, becoming humanity's first true explorers of the frontier between the sun and the stars. In the summer of 1977, humanity launched two spacecraft that were never intended to become the greatest long-distance explorers in history. Their original mission was ambitious enough. The outer planets were approaching a rare alignment that occurs only about once every 176 years. By carefully timing a spacecraft's trajectory, engineers realized it could use the gravity of one giant planet to accelerate toward the next, conserving precious fuel while visiting multiple worlds in a single expedition. It was a celestial opportunity that would not return for generations. The two spacecraft were named Voyager 2 and Voyager 1. Despite their names, Voyager 2 launched first on August 20, 1977. Voyager 1 followed 16 days later on September 5th. Because Voyager 1 took a faster trajectory, it overtook its twin and became the first of the pair to reach the outer solar system. Each spacecraft was remarkably modest by modern standards. They weighed less than a small family car. Their onboard computers possessed only a tiny fraction of the processing power found in an ordinary smartphone today. Their memories were measured in kilobytes rather than gigabytes. Yet every component had been designed with extraordinary care, because once they departed Earth, no repairs would ever be possible. Electricity came not from solar panels but from radioisotope thermoelectric generators. Far from the sun, sunlight becomes too weak to power conventional spacecraft instead. Each Voyager carried plutonium-238, whose natural radioactive decay produced heat. That heat was converted into electricity, allowing the spacecraft to operate continuously, even in regions where sunlight had faded to little more than another bright star. The missions quickly justified decades of planning. Voyager 1 revealed Jupiter in astonishing detail during its flyby in 1979. Its cameras observed swirling storms, delicate cloud structures, volcanic activity on the moon Io, and complex interactions between Jupiter's magnetic field and its surrounding environment. Saturn followed in 1980, where Voyager discovered new rings, intricate atmospheric patterns, and unexpected features among the planet's icy moons. Voyager 2 continued even farther. After visiting Jupiter and Saturn, it became the only spacecraft ever to fly past Uranus in 1986. 7 years later, it completed humanity's only close exploration of Neptune. No other mission has returned to either of those distant ice giants since. These planetary encounters transformed astronomy. Entire textbooks required revision. New moons were discovered. Ring systems proved more intricate than expected. Active geology appeared on worlds once believed to be frozen and lifeless. Each destination revealed that the solar system was more dynamic and diverse than anyone had imagined. Yet something even more extraordinary was quietly unfolding. Every gravitational assist that carried Voyager toward another planet also accelerated it outward. Away from the Sun, after completing their planetary missions, neither spacecraft turned back toward Earth. Instead, they continued onward into the immense darkness beyond the known planets. Their scientific purpose changed. The cameras that had photographed Jupiter's storms and Saturn's rings were eventually switched off. There was little left to photograph in the endless blackness ahead, and every watt of electricity had become precious. Mission controllers gradually powered down instruments that were no longer essential, preserving energy for experiments capable of measuring particles, plasma, magnetic fields, and cosmic radiation. The Voyagers had become something different. They were no longer explorers of planets. They were becoming explorers of space itself. Decade after decade, they continued outward at speeds exceeding 17 kilometers per second. That sounds astonishingly fast by everyday standards. A commercial airliner travels at about 250 meters per second. A rifle bullet moves at roughly 1 kilometer per second. The Voyagers raced through space many times faster than either. And still, on the scale of the solar system, their progress is remarkably slow, even after travelling continuously for more than 40 years. The spacecraft had reached only the outermost regions of the Sun's invisible domain. This alone reveals something profound about cosmic distance. The fastest machines humanity has ever sent into deep space required decades merely to approach the frontier of our own stellar neighbourhood. As they ventured farther from the Sun, their instruments began detecting subtle changes. The solar wind weakened. Its particles became less numerous. Magnetic fields shifted. Meanwhile, energetic cosmic rays arriving from the wider galaxy grew steadily stronger. Scientists had predicted these trends for years. But prediction and observation are not the same. For the first time, direct measurements were arriving from a region no spacecraft had ever entered before. One particularly important milestone was the termination shock. Voyager 1 crossed this boundary in December 2004 at a distance of about 94 astronomical units from the Sun. Voyager 2 encountered it in 2007 at roughly 84 astronomical units. The difference surprised researchers, rather than forming a perfectly symmetrical shell around the solar system. The termination shock appeared irregular, distorted by magnetic fields and changing solar conditions. This was the first clear indication that the heliosphere was more complex than many earlier models had suggested. Beyond the termination shock lay the heliosheath. Here the solar wind had slowed dramatically after losing its supersonic speed. The plasma became hotter and more turbulent. Magnetic fields twisted into unexpected configurations. Conditions changed over distances so enormous that months of spacecraft travel revealed only gradual variations. The heliosheath was not empty. It was a dynamic region where the Sun and the galaxy continuously negotiated their invisible boundary. Then came an even greater moment. On August 25, 2012, Voyager 1 detected a sudden and persistent change. The density of solar particles dropped sharply. Galactic cosmic rays increased significantly. Measurements indicated that the spacecraft had crossed the heliopause, entering a region where the interstellar medium now dominated. Years later, Voyager 2 crossed the heliopause as well. in November 2018, providing an invaluable second set of measurements under different solar conditions. These crossings marked a historic achievement. For the first time, human-built objects were directly sampling interstellar space. It is worth being precise about what this means. Voyager 1 and Voyager 2 entered the local interstellar medium because they moved beyond the heliosphere, where the solar wind no longer governs the surrounding plasma. However, they have not escaped the sun's gravity. They remain on trajectories that are gravitationally linked to the solar system, and are still thought to lie far inside the enormous region associated with the distant Oort cloud. In one sense they have left, in another, they are still very much on the journey. This distinction illustrates an important lesson that has appeared again and again throughout astronomy. Nature often resists simple definitions. A coastline changes with every tide. A forest gradually becomes open grassland. The atmosphere fades into space without a single unmistakable edge. Likewise, the solar system possesses several overlapping boundaries, each meaningful in its own way. The Voyagers also carry something profoundly human. Attached to each spacecraft is a golden phonograph record. It contains sounds from Earth, greetings spoken in dozens of languages, music from different cultures, natural noises such as wind and birdsong, and images encoded for any civilization that might one day discover it. The record is not a realistic attempt at communication. The probability that another civilization will ever encounter either spacecraft is extraordinarily small. Instead, it serves as a time capsule. It represents a quiet statement that a curious species once emerged around an ordinary star and chose to send a small piece of itself into the darkness. Not because it expected an answer, but because exploration is part of its nature. Today, the signals from Voyager 1 require well over 20 hours to reach Earth. Travelling at the speed of light across billions of kilometres, commands sent from mission controllers take just as long to arrive. Conversations with these tiny spacecraft unfold over nearly 2 days, each exchange reminding us how quickly distance overwhelms even light itself. The Voyagers have shown us that the frontier beyond the planets is real. They have confirmed many predictions while revealing unexpected complexities. But perhaps their most important lesson is not about the boundary they crossed. It is about the unimaginable scale that still remains ahead. Even after nearly half a century of continuous travel, humanity's most distant ambassadors have barely begun the voyage toward the nearest stars. If this is how long it takes merely to reach the edge of our sun's magnetic influence, what does that imply about the true challenge of leaving the solar system altogether beyond the heliopause? The character of space changes almost imperceptibly. There is no sudden darkness waiting outside the solar system, no dramatic wall of dust, no brilliant gateway marking the beginning of another realm. If a traveller could accompany Voyager 1, the view through a window would appear almost unchanged. The sun would still shine ahead, though smaller than ever before. The familiar constellations would remain nearly identical. The blackness between the stars would seem just as silent as it did 1 billion kilometres earlier. Yet the environment has become fundamentally different. The particles surrounding the spacecraft no longer originate primarily from the sun. Instead, they belong to the vast interstellar medium that fills the Milky Way. Here, the sun is no longer the dominant force shaping the local plasma. Its magnetic influence has weakened, and the wider galaxy has begun to assert its own quiet presence. It is easy to hear the phrase interstellar space and picture an enormous emptiness. In one sense, that impression is correct. The density of matter between the stars is astonishingly low. A laboratory vacuum on Earth contains vastly more particles than a typical cubic centimetre of interstellar space. If Earth's atmosphere were somehow stretched until it matched that density, it would extend far beyond the orbit of Pluto before becoming as thin. And yet, almost empty is not the same as nothing. Across distances measured in trillions of kilometres, even a handful of atoms becomes meaningful. Most of the interstellar medium consists of hydrogen, the simplest and most abundant element in the universe. Helium is the second most common component. Mixed among them are traces of heavier elements forged inside generations of ancient stars. Tiny dust grains drift through the darkness, carrying carbon, silicates, frozen compounds, and the chemical ingredients from which future stars and planets may one day form. Everything that makes worlds ultimately passes through this quiet ocean. The atoms inside Earth's oceans were once part of earlier generations of stars. The calcium in human bones, the oxygen we breathe, the iron flowing through our blood all originated within stellar furnaces long before the sun itself existed. Those atoms spent millions, and sometimes billions, of years travelling through interstellar space before becoming part of the cloud that eventually collapsed into our solar system. The darkness between the stars is therefore not merely empty space. It is the galaxy's great reservoir of raw material. Clouds slowly gather. Stars ignite. Planets emerge. Stars die. Their material returns to the interstellar medium, where the cycle quietly begins again. Leaving the solar system does not mean entering a barren void. It means entering the environment from which our own home was born. This realization changes the meaning of the journey. When Voyager entered interstellar space, it was not arriving somewhere entirely foreign. In a sense, it was returning to the larger ocean from which the solar system itself had once condensed. But another challenge soon becomes impossible to ignore: distance. It is tempting to think of space travel as primarily an engineering problem. Build a faster engine, carry more fuel, improve the spacecraft. Eventually the stars become reachable. Physics tells a more sobering story. Consider our nearest stellar neighbour. Proxima Centauri lies approximately 4.4 light-years from Earth. A light-year is not a measure of time, but of distance. It is the distance light travels in 1 year, about 9.46 trillion kilometres. Numbers of this size are difficult to appreciate. Suppose an aircraft could somehow fly continuously toward Proxima Centauri without stopping for fuel, maintenance, or weather, even ignoring the impossibility of flying through space. It would require millions of years to arrive. Modern spacecraft perform much better than aircraft. But the conclusion changes surprisingly little. Voyager 1 is moving at roughly 17 kilometers per second relative to the Sun. At that speed, and assuming its trajectory happened to point directly toward Proxima Centauri, the journey would require well over 70,000 years. Of course, Voyager is not actually heading toward Proxima Centauri. It is travelling in an entirely different direction. The comparison simply illustrates the enormous scale involved. Our fastest spacecraft are extraordinarily successful within the solar system. Against interstellar distances, they become almost motionless. The problem becomes even clearer when viewed another way. If the Sun were reduced to the size of a grapefruit, Earth would orbit roughly 15 meters away. Neptune would circle at about half a kilometer. The heliosphere would extend for several kilometers. The nearest star, however, would still be hundreds of kilometers distant. Almost all of the map would consist of empty road. This is one reason astronomers often describe our galaxy as surprisingly sparse. Stars appear crowded in the night sky because we view them from great distances, compressed into a two-dimensional pattern. In reality, neighbouring stars are separated by immense volumes of nearly empty space. The Milky Way contains hundreds of billions of stars, yet each typically occupies its own enormous region of isolation. Even if propulsion technology improved dramatically, another obstacle would remain: energy. Every increase in speed demands additional energy. At everyday velocities, this relationship feels manageable. Doubling the speed of a bicycle requires extra effort. Doubling the speed of an automobile consumes more fuel. Spacecraft obey the same physical laws, but the numbers grow rapidly. Accelerating even a relatively small spacecraft to a significant fraction of the speed of light would require energies that dwarf those used by present-day space missions. The challenge is not merely building a stronger engine, it is generating, storing, and directing enormous amounts of energy with extraordinary precision and reliability. Then there is the question of fuel. Traditional rockets must carry the propellant needed for nearly every maneuver. Unfortunately, propellant itself has mass. More fuel requires a larger rocket. A larger rocket requires still more fuel to accelerate the added fuel. This feedback, described mathematically by the Tsiolkovsky rocket equation, has shaped every space mission ever flown. Engineers have become remarkably skilled at working within these constraints. Multi-stage rockets discard empty tanks to reduce mass. Gravity assists borrow momentum from planets. Highly efficient ion engines trade thrust for endurance. Yet the underlying limitation remains. Chemical propulsion, remarkable though it is, was developed for journeys between planets, not between stars. This is why so many proposed interstellar missions rely upon fundamentally different approaches. Solar sails attempt to harness the pressure of sunlight. Powerful lasers might one day accelerate ultralight spacecraft. Nuclear fusion could potentially release far more energy than chemical reactions. More speculative concepts consider antimatter, whose annihilation converts mass directly into energy with extraordinary efficiency. Each approach offers genuine scientific promise. Each also confronts daunting engineering challenges that remain unsolved. The farther one studies interstellar travel, the more the problem expands. Distance leads to energy. Energy leads to propulsion. Propulsion leads to materials. Materials lead to heat management, reliability, communication, radiation protection, and decades, perhaps centuries, of uninterrupted operation. Every solution opens another question. Even communication itself becomes part of the challenge. Radio signals travel at the speed of light, the fastest speed permitted by our current understanding of physics. Yet when distances are measured in light years, conversation becomes impossible in any ordinary sense. A message sent to a crew orbiting Proxima Centauri would not receive a reply for more than 8 years. Advice, emergencies, discoveries, even simple greetings would unfold across nearly a decade. Interstellar exploration demands not only advanced technology, but an entirely different relationship with time. The universe seems almost to encourage patience. Stars evolve over millions of years. Galaxies change over billions. Against that backdrop, the decades required for Voyager to reach interstellar space begin to appear surprisingly brief. The farther humanity looks beyond the solar system, the more one realization quietly returns. The challenge is not simply crossing a boundary, it is adapting to a universe whose natural scales are vastly larger than the timescales around which human civilization has evolved. And once we begin viewing our journey through that larger perspective, another question naturally emerges. Perhaps the greatest obstacle is not the emptiness between the stars, but whether the laws of physics themselves permit us to cross it in any practical way. For centuries, the greatest obstacle to leaving the solar system seemed obvious. It was distance. The planets were separated by hundreds of millions, and sometimes billions, of kilometers. The stars lay vastly farther away still. If humanity could simply build faster spacecraft, it seemed reasonable to believe that the problem would gradually disappear, just as faster ships once shrank the oceans of Earth. The deeper astronomers and physicists explored the problem, the more they realized that distance was only the beginning. The central mystery is not whether the solar system has an edge. We now know that it does, although that edge depends on which physical boundary we choose to define. The greater mystery is why escaping our stellar neighborhood remains so profoundly difficult, even after more than a century of astonishing technological progress. The answer does not lie in a single obstacle. It lies in the quiet cooperation of several fundamental laws of nature. Each one seems manageable on its own. Together, they form one of the most formidable barriers humanity has ever encountered. The first is energy. Every spacecraft begins its journey by borrowing energy from Earth. Chemical fuel stores energy inside molecular bonds. When those bonds are broken through combustion, expanding gases rush from the rocket's engines, pushing the vehicle upward according to Newton's third law. Every launch, from the earliest rockets to the largest missions ever flown, follows this same fundamental principle. Chemical propulsion is extraordinarily powerful. For escaping Earth's gravity, it remains unmatched in practicality. But chemistry has limits. The amount of energy released by chemical reactions is tiny compared with the energies associated with nuclear processes. A kilogram of ordinary rocket fuel contains impressive amounts of usable energy by everyday standards. A kilogram of uranium undergoing nuclear fission contains millions of times more. Fusion, the process that powers the sun, offers still greater energy potential for future propulsion systems. Though practical fusion engines remain beyond current engineering capabilities, this comparison reveals something important. The challenge of interstellar travel is not simply that rockets are too small. It is that the energy densities required for rapid journeys between stars far exceed those available from the propulsion methods that currently carry humanity into space. Then comes mass. Every spacecraft contains more than instruments and engines. It requires structure, power systems, communication equipment, computers, thermal control, fuel if human passengers are involved. Additional necessities appear almost immediately: air, water, food, radiation shielding, medical supplies, living space, waste recycling, redundancy for every critical system. Every kilogram improves the mission's chances of success. Every kilogram also demands additional energy to accelerate. This is one reason robotic spacecraft have ventured so much farther than humans. Voyager weighs only a fraction of what would be required to sustain even a single astronaut for years, let alone decades. Machines can tolerate isolation. They require no oxygen, no sleep, no protection from loneliness, no return journey. Humans carry remarkable advantages in creativity and adaptability. But biologically, we're extraordinarily demanding travelers. Time introduces another layer of complexity. The Apollo astronauts reached the moon in only a few days. Mars missions would require many months. A journey to the outer planets stretches into years. Interstellar travel, using present-day propulsion, extends into centuries or millennia. This changes the nature of exploration itself. A scientific expedition lasting 2 weeks can be directed from Earth. One lasting 30 years must anticipate technologies that do not yet exist. A mission lasting hundreds of years would almost certainly outlive the civilization that launched it, even if every engineering challenge could somehow be solved. Another question quietly emerges: who receives the results? Human societies evolve rapidly. Languages change. Governments rise and fall. Scientific priorities shift. Technologies become obsolete. The first radio broadcast occurred only a little more than a century ago. Voyager's journey into interstellar space has already lasted nearly half that time. Now imagine planning a mission expected to arrive after 1,000 years. Such projects force us to think not merely as engineers, but as caretakers of knowledge across generations. Nature presents another obstacle that is almost invisible: radiation near Earth. Several layers of protection quietly surround us. Our atmosphere absorbs harmful ultraviolet light and energetic particles. Earth's magnetic field deflects many charged particles before they reach the surface. The heliosphere reduces a significant fraction of galactic cosmic rays before they approach the inner solar system. Beyond these shields, conditions become increasingly demanding. Galactic cosmic rays consist largely of high-energy atomic nuclei, accelerated by some of the most energetic events in the universe, including supernova explosions. Many travel at speeds approaching that of light. When they strike spacecraft materials, they can produce cascades of secondary particles capable of damaging electronics and living tissue alike, unlike sunlight, which can often be blocked with relatively thin shielding. The most energetic cosmic rays are extraordinarily difficult to stop. Adding thicker shielding is not always an effective solution. Heavy materials can produce additional secondary radiation when struck by extremely energetic particles. Engineers must carefully balance protection, mass, and mission requirements. Radiation therefore becomes both a biological and an engineering problem. Then there are microscopic hazards. Interstellar space is remarkably empty. Yet remarkably empty does not mean perfectly empty. Tiny grains of dust travel through the galaxy at enormous relative speeds. At everyday velocities, a grain of sand seems harmless. At tens of thousands of kilometers per second, even particles smaller than a grain of pollen can release tremendous amounts of energy upon impact. Fortunately, spacecraft traveling at Voyager's speed face relatively modest risks. Future spacecraft moving at a significant fraction of the speed of light would encounter a very different environment. The faster a spacecraft travels, the more dangerous even the smallest particles become. Protecting a vehicle against countless microscopic impacts over many years represents another unsolved engineering challenge. Communication, too, grows increasingly fragile. Radio waves weaken steadily as they spread through space. By the time Voyager's faint transmissions reach Earth, they are unimaginably weak. Engineers rely on giant antennas, sophisticated signal processing, and extraordinarily sensitive receivers to detect them. Even then, the data rate is astonishingly slow. Images that once took minutes to transmit near Jupiter would require far longer across today's immense distances. An interstellar mission would demand communication systems capable of operating across light years while using limited onboard power. The farther the spacecraft travels, the quieter its voice becomes. Navigation also changes. Within the solar system, spacecraft can use the sun, planets, and distant stars to determine their orientation and trajectory with extraordinary precision. Between the stars, familiar landmarks become fewer. Tiny errors accumulated over decades could place a spacecraft millions of kilometers away from its intended path. Precision that seems almost unimaginable by human standards becomes routine. Yet perhaps the deepest challenge is more subtle than any of these. It concerns the laws of physics themselves. Albert Einstein's theory of special relativity tells us that no object possessing mass can be accelerated to the speed of light. As an object's speed approaches that cosmic limit, the energy required to accelerate it further rises dramatically. Reaching half the speed of light is difficult. Reaching 90% is vastly harder. Approaching the speed of light itself demands energy that increases without bound. This is not an engineering limitation. It is a consequence of our current understanding of space-time. Many imaginative ideas have been proposed over the decades. Warp drives, traversable wormholes, exotic space-time geometries. Most arise naturally from legitimate mathematical solutions within general relativity. But mathematics alone is not evidence that nature permits such phenomena to exist in useful forms. Many require hypothetical forms of matter or energy that have never been observed. Others remain internally consistent yet far beyond experimental verification. Astronomers and physicists therefore distinguish carefully between mathematical possibility and physical reality. This distinction is essential. Science advances by exploring bold ideas. It advances equally by demanding evidence before accepting them. Today, no experimentally confirmed technology allows travel faster than light. No observation has demonstrated that the fundamental speed limit imposed by relativity can be bypassed. That does not prove such possibilities are forever impossible. It simply reflects the current frontier of knowledge. The central mystery therefore becomes clearer. Leaving the solar system is not prevented by one enormous barrier standing in our way. Instead, countless smaller realities accumulate. Distance, energy, mass, time, radiation, communication, materials, relativity. Each is governed by well-tested physical laws. Each seems reasonable in isolation. Together, they shape the quiet architecture of our cosmic isolation. And yet, despite these immense difficulties, scientists continue proposing new ways forward. Some rely on technologies already under development. Others extend cautiously into theoretical physics. Each attempts to answer the same enduring question. If nature has made the journey so difficult, has it also left behind a path that we have not yet learned to recognize? Every great scientific mystery begins in much the same way, not with certainty, but with measurement. Before astronomers can explain a phenomenon, they must first establish what the universe is actually doing. Theories may change over time, assumptions may prove incomplete, elegant ideas may eventually be discarded, but careful observations remain the foundation upon which every successful explanation is built. The question of leaving the solar system is no exception. It is tempting to discuss the subject entirely in terms of engineering or imagination. Faster rockets, more powerful engines, future technologies. Yet long before scientists ask how humanity might travel beyond the sun, they first ask a quieter question. What does the frontier actually look like? Unlike the surfaces of planets, the outer solar system cannot simply be photographed. There are no mountains marking the heliopause, no glowing ring surrounding the sun, no signpost suspended in the darkness announcing the beginning of interstellar space. Instead, astronomers must rely on instruments capable of measuring things that human senses cannot perceive directly: charged particles, magnetic fields, plasma density, cosmic radiation, the direction and energy of atoms moving through space. These invisible measurements gradually reveal the shape of an otherwise invisible environment. One of the earliest clues arrived decades before the Voyager spacecraft approached the heliosphere's boundary, in the late 1950s and early 1960s. The first space probes leaving Earth's immediate surroundings detected a steady stream of charged particles flowing away from the Sun. This confirmed the existence of the solar wind, a prediction made by astrophysicist Eugene Parker. At the time, Parker's proposal was controversial. Many scientists believed the Sun's atmosphere should remain relatively static. Parker argued that it could not. The corona, the Sun's outer atmosphere, is so hot that its particles possess enough energy to escape continuously into space. According to his calculations, this outflow should accelerate until it became a supersonic wind filling the solar system. Early spacecraft confirmed that prediction. What had once been a theoretical model became an observed reality. The importance of this discovery cannot be overstated. Without the solar wind, there would be no heliosphere. Without the heliosphere, there would be no distinct magnetic bubble surrounding our planetary system. Every later mission exploring the solar system has relied, directly or indirectly, on this understanding. As spacecraft travelled farther outward, another pattern emerged. The solar wind did not remain constant. Its speed varied. Its density fluctuated. Its magnetic field twisted into an enormous spiral because the Sun rotates while continuously releasing plasma. This structure is known as the Parker spiral. Rather than extending outward in perfectly straight lines, the Sun's magnetic field wraps gently through the solar system. Resembling water sprayed from a rotating garden sprinkler, this spiral influences how energetic particles travel through space. It also affects the way cosmic rays enter the heliosphere. The result is a dynamic magnetic environment that changes continuously as the Sun rotates approximately once every 27 days and progresses through its 11-year activity cycle. Observations soon revealed that the outer solar system is not simply quieter than the inner one. It is more variable. Solar storms launched near the Sun may require days or even weeks to reach Earth. Far beyond Neptune, their effects can continue propagating for months. The frontier of the heliosphere is therefore shaped not only by distance, but by events occurring millions of kilometers away on the Sun itself. Then came the Voyager missions. As Voyager 1 and Voyager 2 journeyed outward, their instruments continuously sampled the surrounding plasma. Scientists watched for several key indicators. How many charged particles originated from the solar wind? How many arrived from interstellar space? How strong was the magnetic field? How did its direction change? How dense was the surrounding plasma? Each measurement represented one small piece of a much larger puzzle. No single observation could identify the heliopause. Instead, researchers looked for a consistent pattern across multiple independent instruments. When Voyager 1 approached the outer heliosphere, something remarkable occurred. The intensity of low-energy particles associated with the solar wind decreased dramatically. At nearly the same time, high-energy galactic cosmic rays increased and remained elevated. This was precisely the trend expected if the spacecraft had entered the local interstellar medium. Yet one measurement complicated the picture. Scientists expected the magnetic field to rotate sharply after crossing the heliopause. Initially, Voyager detected only a modest change in direction. Some researchers wondered whether the spacecraft had truly crossed the boundary at all. Others proposed that the heliopause itself might be more complicated than earlier theoretical models suggested. Over time, additional observations resolved much of the uncertainty. Measurements of plasma density indicated that Voyager was indeed surrounded by material characteristic of interstellar space. The magnetic field appeared to connect more smoothly across the boundary than many earlier models had predicted. Nature once again proved more subtle than simple diagrams. Voyager 2 provided an invaluable comparison. Unlike its twin, Voyager 2 still carried a functioning plasma instrument when it crossed the heliopause in 2018. This allowed scientists to directly measure changes in solar wind particles as they disappeared and interstellar particles became dominant. Although the overall transition resembled Voyager 1's experience, important differences also appeared. The heliosphere was not perfectly symmetrical. Local conditions varied. Solar activity had changed. The frontier itself seemed to breathe and shift over time. Two spacecraft crossing at different locations and different years observed similar boundaries, yet not identical ones. This strengthened confidence in the broad physical picture while revealing unexpected complexity. Other spacecraft have contributed important pieces as well. NASA's Interstellar Boundary Explorer, known as IBEX, never travelled anywhere near the heliopause. Instead, it remained near Earth while observing energetic neutral atoms arriving from the outer solar system. These particles form when charged particles exchange electrons with neutral atoms, allowing them to travel in straight lines unaffected by magnetic fields. By mapping these particles across the sky, IBEX effectively created an indirect image of the heliosphere. One discovery surprised nearly everyone. Rather than observing a smooth glow surrounding the solar system, IBEX detected a long, bright ribbon stretching across much of the sky. This IBEX ribbon had not been predicted by earlier models. Even today, astronomers continue investigating exactly why it forms. The leading explanation connects it to interactions between the heliosphere and the magnetic field of the surrounding interstellar medium. If correct, the ribbon provides another clue about how our solar system interacts with the galaxy beyond. NASA's Interstellar Mapping and Acceleration Probe, or IMAP, has been designed to extend this work by producing even more detailed maps of the heliosphere through energetic neutral atoms, rather than physically travelling to the boundary. Missions like IBEX and IMAP demonstrate another strength of astronomy. Sometimes scientists learn about distant places not by visiting them directly, but by carefully studying the particles that quietly arrive from afar. Ground-based observatories also contribute. Although they cannot observe the heliopause directly, detectors on Earth continuously monitor cosmic rays reaching our atmosphere. Long-term variations in cosmic ray intensity reveal changes in solar activity and the shielding provided by the heliosphere. These measurements, collected over decades, complement observations made by spacecraft scattered throughout the solar system. No single instrument tells the whole story. The picture emerges only when many independent observations are combined. This is one of science's greatest strengths. Confidence grows not because one measurement is perfect, but because different methods converge towards the same conclusion. The solar wind exists. The heliosphere surrounds the solar system. The heliopause marks a transition into interstellar space. The boundary changes over time. Its structure is more complicated than early models suggested. These conclusions rest upon decades of consistent evidence gathered from multiple spacecraft, telescopes, detectors, and theoretical studies. Yet careful measurement also reveals something equally important. Evidence does not answer every question. Astronomers can measure the solar wind with remarkable precision. They can estimate the size of the heliosphere. They can model the surrounding interstellar medium. But measurements alone do not tell us the best way to cross these immense distances. For that, scientists must move from observation to explanation, comparing competing ideas about how future civilizations might one day travel beyond the sun's distant frontier. Once scientists understand the problem, a different question naturally follows. If the distances are real, if the measurements are accurate, and if the laws of physics appear as demanding as they seem, then how might humanity eventually leave the solar system? This is where astronomy gradually gives way to engineering. Not engineering as it exists today, but engineering stretched toward the limits permitted by known physics. For more than a century, researchers have proposed remarkably different approaches to deep space travel. Some have already flown in limited form, others remain ambitious research projects. A few exist only as mathematical possibilities, waiting to discover whether nature allows them to become reality. The important distinction is that none of these ideas begins with fantasy. Each attempts to solve a specific physical problem. The question is not whether they are imaginative. The question is whether they are supported by evidence, whether they obey established physical laws, and whether they appear achievable with technologies that humanity could plausibly develop. The oldest and most familiar approach is the chemical rocket. Every human being who has travelled into space has relied upon chemical propulsion, so has every robotic spacecraft launched from Earth. Its strengths are well understood. Chemical rockets produce enormous thrust. They can overcome Earth's gravity. They are reliable enough to launch satellites, scientific missions, and astronauts. But they are also approaching their practical limits. The chemistry itself cannot be made dramatically more energetic. Engineers continue improving efficiency through better fuels, lighter materials, and smarter designs. Yet no foreseeable chemical rocket can reduce an interstellar journey from tens of thousands of years to decades. For travel between planets, chemistry is sufficient. For travel between stars, it is almost certainly not. The next family of ideas already operates quietly throughout the solar system. Ion propulsion. Unlike chemical engines, ion thrusters do not produce explosive bursts of thrust. Instead, they accelerate electrically charged atoms using electric fields. Each individual push is tiny. A sheet of paper resting on your hand exerts more force than some ion engines, yet in the vacuum of space, where there is no air resistance, that gentle push can continue for months or even years. The result is remarkable. Spacecraft equipped with ion propulsion gradually reach much higher speeds than chemical rockets alone could provide. NASA's Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres, demonstrated just how effective continuous low-thrust propulsion can be. Even so, ion engines remain limited by their power source. Today's systems rely primarily on solar electricity. Far from the Sun, solar panels receive steadily less light. Beyond Jupiter, they become increasingly impractical unless they are made extraordinarily large. Nuclear electrical systems could extend their range, but the improvement would still fall well short of what interstellar travel demands. Another elegant possibility requires almost no fuel at all: a solar sail. Light may appear weightless, but photons carry momentum. When sunlight strikes a reflective surface, it transfers a minute amount of that momentum. For an ordinary object, the effect is imperceptible. For an enormous, ultra-thin sail floating in space, it becomes measurable. Japan's Ikaros mission successfully demonstrated this principle in 2010. The spacecraft slowly accelerated using nothing more than sunlight. The concept is beautifully simple. As long as sunlight continues striking the sail, acceleration continues. There is no need to carry vast quantities of propellant. Unfortunately, sunlight weakens rapidly with distance. By the time a spacecraft reaches the outer solar system, the pressure exerted by sunlight has fallen dramatically. The sail continues working, but ever more gently. Some researchers therefore propose replacing the sun with lasers, instead of allowing sunlight to push the sail. Powerful laser arrays based near Earth could concentrate enormous amounts of energy onto a lightweight spacecraft. One of the most widely discussed concepts is breakthrough starshot. Rather than accelerating a massive spacecraft carrying astronauts, Starshot envisions sending miniature probes weighing only a few grams. Driven by extremely powerful Earth-based lasers, these tiny spacecraft might eventually reach roughly 20% of the speed of light. At that velocity, the journey to Alpha Centauri could take about 20 years instead of tens of thousands. It is an extraordinary proposal. It is also an immense engineering challenge. The laser system required does not yet exist. Keeping the beam accurately focused across millions of kilometers presents formidable technical difficulties. The sail must survive tremendous acceleration while remaining almost perfectly stable. Communication from such tiny spacecraft across light years remains another unsolved problem. Nevertheless, every element of the proposal rests upon known physics. No new laws of nature are required, only engineering on an unprecedented scale. Many scientists therefore regard Starshot as ambitious, but fundamentally plausible. Nuclear propulsion offers another path. Unlike chemical reactions, nuclear processes release vastly greater amounts of energy. Several concepts have been studied over the decades. Nuclear thermal rockets would heat hydrogen using a nuclear reactor before expelling it through a nozzle. Such engines could roughly double the efficiency of today's best chemical rockets. NASA and other agencies continue exploring this possibility for future missions to Mars. For interstellar travel, however, even greater performance may be necessary. Fusion propulsion attempts to harness the same process powering the Sun. When light atomic nuclei combine, enormous energy is released. If engineers eventually learn to control sustained fusion efficiently inside spacecraft engines, travel times across the solar system could shrink dramatically. Concepts such as Project Daedalus, studied by the British Interplanetary Society during the 1970s, explored whether an unmanned fusion-powered spacecraft might someday reach another star within a human lifetime. The study demonstrated that no obvious physical law forbids such a mission. It also revealed how extraordinarily difficult building such a vehicle would be. Controlled fusion remains one of humanity's greatest scientific and engineering challenges, even for producing electricity on Earth. Building a reliable fusion spacecraft is considerably more demanding. Still more energetic is antimatter, whenever matter and antimatter meet. Nearly all of their mass converts directly into energy according to Einstein's famous relationship between mass and energy. No known fuel contains greater theoretical energy density. Unfortunately, antimatter is extraordinarily rare. Tiny amounts can be produced inside particle accelerators, but manufacturing even microscopic quantities requires enormous energy. Storing antimatter safely presents another major challenge because it annihilates immediately upon touching ordinary matter. At present, antimatter propulsion remains firmly in the realm of theoretical engineering rather than practical technology. Then there are ideas that attract enormous public attention. Warp drives, wormholes, space bending instead of space crossing. These concepts deserve careful treatment because they illustrate an important difference between a mathematical possibility and experimental science. General relativity describes gravity as the curvature of space-time itself. Within Einstein's equations, certain highly unusual solutions appear possible. One famous example is the Alcubierre warp drive, proposed in 1994. Rather than moving a spacecraft through space faster than light, the idea suggests expanding space behind the vehicle while contracting space ahead of it. Locally, the spacecraft would never exceed the speed of light. Globally, the destination could be reached more quickly because space-time itself would carry the spacecraft. It is an elegant mathematical solution. It is not an established technology. Current analyses indicate that such concepts would likely require forms of exotic matter or negative energy unlike anything known to exist in usable quantities. Some later studies have suggested modifications that reduce the enormous energy requirements originally calculated. Even so, no experiment has demonstrated that a warp drive can be constructed. The situation is similar for traversable wormholes. General relativity permits certain theoretical space-time tunnels connecting distant regions. Whether stable wormholes exist in nature remains entirely unknown. No observational evidence has confirmed their existence. No spacecraft has ever approached one. No experiment has shown that such structures can be created or maintained. For these reasons, astronomers classify warp drives and traversable wormholes not as accepted engineering proposals, but as speculative consequences of mathematical physics. This distinction matters. Speculation has a valuable place in science. Many successful discoveries began as bold hypotheses, but speculation becomes knowledge only after surviving observation and experiment. Today, the evidence supports a more modest conclusion. Humanity possesses several promising avenues for significantly improving deep space travel. Electric propulsion, nuclear propulsion, laser-driven sails, advanced materials, autonomous spacecraft. Each could dramatically expand our reach within the solar system. Some may eventually open the path toward nearby stars. At the same time, no existing technology has solved the fundamental challenge of transporting large crews across interstellar distances within a human lifetime. That remains an open problem. Yet suppose, for a moment, that one of these approaches ultimately succeeds. Suppose future generations develop a spacecraft capable of leaving the solar system far more rapidly than Voyager ever could. Would escaping the sun finally mean escaping the greatest challenges of the journey? Or would crossing into interstellar space simply reveal an entirely new set of obstacles waiting beyond the frontier? The history of science is filled with moments when solving one problem revealed another that had been quietly waiting beyond it. Crossing an ocean did not end exploration. It introduced new continents. Reaching the moon did not complete the story of spaceflight. It opened the possibility of traveling to other worlds. Leaving the solar system, if humanity eventually achieves it, would almost certainly follow the same pattern. For a moment, let us consider a carefully grounded thought experiment. Not one that requires faster-than-light travel or unknown laws of physics, but one that stays within the boundaries of what modern science considers at least physically conceivable. Suppose that, many generations from now, engineers succeed in building an advanced robotic spacecraft. Perhaps it is driven by fusion, perhaps by a powerful laser sail, perhaps by another propulsion system that has not yet been perfected but remains consistent with established physics. Whatever the technology, assume it reaches a speed of roughly 20% of the speed of light. similar to the long-term goal proposed by projects such as Breakthrough Starshot. At that velocity, the journey through the solar system changes dramatically. The planets pass almost too quickly to observe. Earth disappears behind the spacecraft within minutes. The orbit of Mars is crossed in less than half an hour. Jupiter's immense system arrives after only a few hours. Neptune, which Voyager required more than a decade to reach, would be left behind in roughly a single day. For the first time, the vast architecture of the solar system begins to resemble a destination that can be crossed rather than merely endured. Yet something unexpected happens. Even after all the planets have disappeared into the darkness behind, almost nothing appears to change. The view outside remains astonishingly familiar. The stars do not suddenly grow larger. Constellations barely shift. The sun, although steadily shrinking into another brilliant point of light, remains by far the brightest object in the sky for a very long time. This illustrates one of the quiet surprises of cosmic scale. The planetary system occupies only a tiny region compared with the distances separating neighbouring stars. Leaving the solar system does not immediately create the feeling of arriving somewhere new. Instead, it creates the experience of entering an almost unimaginable emptiness. As the spacecraft moves farther from the sun, another transformation begins. The heliosphere eventually falls behind. The surrounding particles now belong almost entirely to the interstellar medium. Cosmic rays become more numerous. The sun's magnetic influence weakens. The spacecraft is no longer travelling inside a bubble created by its parent star. It has entered the shared environment of the galaxy. This may sound like a simple change of location. In reality, it alters nearly every aspect of the mission. Navigation becomes more demanding. Within the solar system, spacecraft often use the positions of planets, the sun, and precisely measured radio signals from Earth to determine their location. In interstellar space, those familiar reference points gradually lose their usefulness. The spacecraft must increasingly rely upon distant stars, quasars, and extraordinarily accurate onboard clocks. Even a tiny navigational error becomes significant over years of travel. Consider a deviation of only 1/1,000,000th of a degree. On Earth, such an angle seems almost impossible to notice. Across several light years, however, that minute error could cause a spacecraft to miss its intended destination by millions of kilometers. Precision that already appears astonishing today would need to become routine. Communication evolves as well. At 20% of the speed of light, the spacecraft itself is moving rapidly by human standards. Its radio signals, however, still travel at the speed of light. Nothing changes that limit. If the spacecraft is 1 light year from Earth, every message requires at least 1 year to arrive. A simple exchange becomes impossible. Mission control can no longer guide the spacecraft moment by moment. Instead, the vehicle must become increasingly autonomous. It must identify problems, repair faults when possible, adjust its trajectory, protect itself from unexpected hazards. In many respects, it must become an independent scientific explorer rather than a remotely controlled machine. Artificial intelligence therefore becomes not merely convenient, but essential. The farther humanity reaches into interstellar space, the less practical continuous human supervision becomes. Future spacecraft may need to make thousands of decisions before Earth even learns that the first question arose. The environment itself also grows more demanding. Although interstellar space is extraordinarily empty, it is not perfectly so. Atoms drift silently through the galaxy. Tiny dust grains move on their own galactic orbits. At ordinary spacecraft speeds, these particles represent only a modest concern. At 20% of the speed of light, they become something entirely different. Energy depends not only on mass but also on velocity. A microscopic grain of dust striking the spacecraft at such tremendous speed releases energy comparable to a much larger impact at everyday velocities. Engineers therefore study advanced shielding concepts capable of protecting future interstellar probes. Some proposals involve sacrificial outer layers designed to absorb impacts gradually. Others consider electromagnetic fields that might deflect charged particles. Each solution introduces additional complexity. Every improvement in speed creates new engineering challenges that slower spacecraft never encounter. The scientific opportunities, however, become extraordinary. For the first time, direct measurements of the local interstellar medium could be collected continuously rather than during brief crossings near the heliopause. astronomers could examine the structure of galactic magnetic fields with unprecedented detail. They could study cosmic rays before they are modified by the heliosphere. They could measure the distribution of interstellar dust across vast distances. Perhaps most importantly, they could compare these measurements with observations made near other stars in the future. Only then would we begin understanding whether the Sun's environment is typical or unusual. Eventually, after decades of travel, another point of light begins changing almost imperceptibly. One particular star grows brighter than the rest. Its position shifts slightly against the distant background. Slowly, almost patiently, it transforms from one star among countless others into an approaching destination. This is another remarkable consequence of interstellar travel. The stars that seem fixed throughout a human lifetime are not fixed at all. Every star in the galaxy moves. Our Sun travels around the Milky Way. Nearby stars follow their own independent paths. The constellations familiar today are temporary arrangements that change over thousands and millions of years. A spacecraft traveling between stars would witness that gradual transformation directly. The sky itself would evolve. This reminds us that the night sky visible from Earth is not universal. It is simply the view from one small location during one brief moment in cosmic history. Move far enough through the galaxy, and entirely new patterns emerge. New horizons replace old ones. The familiar heavens slowly disappear. Yet perhaps the greatest surprise is psychological rather than physical. From Earth, the solar system feels immense. From interstellar space, it becomes astonishingly small. The orbit of Neptune vanishes into invisibility. The heliosphere contracts into an unseen bubble surrounding a single ordinary star. The Sun itself joins hundreds of billions of other stars scattered across the Milky Way. Everything humanity has ever built, every language ever spoken, every work of art, every scientific discovery, every generation of our species, all remain within an almost invisible region surrounding one star among many. Leaving the solar system therefore changes more than geography. It changes perspective. The journey reveals that what once seemed to be the whole of our cosmic neighborhood is, in galactic terms, only the smallest beginning, and that realization naturally leads to an even broader question. If our solar system is merely one tiny bubble, drifting through a galaxy filled with hundreds of billions of stars, then how does our struggle to leave home fit into the much larger story of the Milky Way itself? The farther our perspective expands, the smaller the solar system becomes. From Earth's surface, the planets seem to define the architecture of the universe. Ancient civilizations built calendars around their movements. Early astronomers carefully traced their paths across the sky, believing that the wandering lights represented the limits of the known cosmos. Even today, when we picture space, it is often the planets that first come to mind. But the solar system is not the universe. It is not even an especially large part of our own galaxy. It is one planetary system orbiting one ordinary star within the Milky Way. Itself only one galaxy among hundreds of billions spread across the observable universe. Understanding why leaving the solar system is so difficult requires placing it inside this much larger setting. The Milky Way is an immense spiral galaxy, measuring roughly 100,000 light-years across. Its graceful spiral arms are outlined by young, luminous stars and vast clouds of gas where new generations of suns continue to form. Between those arms lie older stellar populations, quieter regions where countless stars continue their slow journeys around the galactic center. Our Sun occupies neither the crowded core nor the galaxy's outermost edge. Instead, it resides within a minor spiral feature known as the Orion Spur, roughly 26,000 light-years from the galactic center. This location is remarkably ordinary. The Sun is not unusually massive. It is not exceptionally bright. It does not occupy a privileged position among the galaxy's hundreds of billions of stars. It is one average member of a vast population. That ordinariness has profound consequences. Most stars likely possess environments that differ in detail but resemble ours in broad physical principles. Many are surrounded by planets. Many produce stellar winds. Many carve out protective bubbles similar to the heliosphere. The challenge of leaving one's home star may therefore be common throughout the galaxy. The heliosphere, impressive though it is only one example of a much broader phenomenon. Every star continuously interacts with its surroundings. Some stars generate winds far stronger than the sun's. Young, massive stars can produce violent outflows capable of sculpting enormous cavities within surrounding clouds of gas. Tiny red dwarf stars, although much smaller, often unleash powerful flares that dramatically affect nearby planets. Each stellar system establishes its own balance with the surrounding interstellar medium. Each creates a different frontier between itself and the galaxy. In that sense, the Milky Way is filled with overlapping stellar bubbles. Some are large, some are small, some collide, some evolve as their parent stars age. The galaxy is not simply a collection of isolated stars. It is a continuously changing network of interacting environments. The Sun itself does not remain within the same surroundings forever. As it orbits the Milky Way, it passes through regions of differing gas density, magnetic field strength, and stellar population. Over millions of years, the local interstellar environment gradually changes. The heliosphere likely changes with it. Scientists have even investigated whether passages through denser interstellar clouds might compress the heliosphere significantly, allowing more galactic cosmic rays to penetrate the inner solar system. Such ideas remain active areas of research. Current evidence suggests that the heliosphere responds dynamically to its galactic surroundings, though many details remain uncertain. This illustrates an important principle. The solar system is not separate from the Milky Way. It is immersed within it. The galaxy influences our stellar environment just as the Sun influences the planets. Scale after scale, the universe reveals nested systems rather than isolated objects. The same pattern appears in the birth of stars. Long before the Sun existed, a vast molecular cloud drifted through one of the Milky Way's spiral regions. Gravity slowly gathered parts of that cloud into denser clumps. Eventually one collapsed under its own weight. The central temperature rose. Hydrogen fusion ignited. The Sun was born. Around it, a rotating disk of gas and dust gradually assembled into planets, moons, asteroids, and comets. This process is no longer merely theoretical. Modern observatories have photographed protoplanetary disks surrounding young stars throughout our galaxy. The Atacama Large Millimeter Submillimeter Array, known as ALMA, has revealed striking rings and gaps where planets appear to be forming. The James Webb Space Telescope has extended these observations with extraordinary sensitivity, allowing astronomers to study the chemistry of young planetary systems in unprecedented detail. These observations carry an important implication. The solar system is not unique in possessing planets. Thousands of exoplanets have now been confirmed around other stars. Many additional candidates continue to be discovered. Some orbit close to their stars. Others travel on highly elongated paths. Some are gas giants larger than Jupiter. Others appear rocky and comparable in size to Earth. No two planetary systems examined so far look exactly alike. Nature appears remarkably creative. Yet despite their diversity, they all share one characteristic. Everyone is separated from its nearest neighbours by immense interstellar distances. The challenge confronting humanity is therefore not an unusual accident. It is a natural consequence of how galaxies are built. Stars require enormous separations. If they formed much closer together, their mutual gravity could destabilize planetary orbits. Frequent close encounters would disrupt developing systems. Stable environments capable of supporting long-lived planets might become much rarer. Ironically, the very distances that make interstellar travel so difficult may also help create the stable conditions under which civilizations can emerge. Isolation becomes both obstacle and protection. The same perspective transforms our understanding of motion. From Earth, the Sun appears almost stationary. In reality, everything is moving. Earth circles the Sun at about 30 kilometers per second. The Sun circles the galaxy at roughly 220 kilometers per second. The Milky Way itself moves relative to neighboring galaxies. Our local group of galaxies travels through the larger cosmic web. Even the cosmic microwave background provides a reference frame against which these enormous motions can be measured. There is no universal state of rest. Every journey takes place within layers of motion already in progress. This has practical consequences for interstellar travel. The nearest stars are not fixed targets. By the time a spacecraft traveling for centuries arrives, its destination will have moved. Fortunately, astronomers can calculate stellar motions with remarkable precision. The European Space Agency's Gaia mission has measured the positions, distances, and motions of more than 1 billion stars. Its observations allow scientists to predict how nearby stellar neighborhoods will evolve over long periods. Future interstellar navigation will rely heavily upon such measurements. The destination is never standing still. The traveler and the destination are both moving through the galaxy together. Perhaps the most humbling realization emerges from this broader view. The Milky Way itself is not permanent. Stars continue forming. Others exhaust their fuel. Supernovae enrich the interstellar medium with heavy elements. Small satellite galaxies merge with larger ones. Over billions of years, the entire structure evolves. Roughly 4 to 5 billion years from now, the Milky Way and the Andromeda Galaxy are expected to undergo a gradual merger. Their stars will mostly pass one another without direct collisions because interstellar distances are so vast. The galaxies will reshape themselves through gravity, eventually forming a much larger system. By then, our own Sun will also be approaching the final stages of its life. The timescales involved are almost beyond comprehension. Human civilization spans only a tiny fraction of one galactic orbit. Recorded history occupies an even smaller fraction. The Voyager missions, remarkable though they are, represent scarcely the briefest moment within the life of the Milky Way, yet they are part of the same continuing story. A young technological species has begun measuring the boundaries of its stellar home while slowly discovering that those boundaries are woven into much larger cosmic structures. The mystery of leaving the solar system is therefore no longer only about propulsion. It becomes a question about our place within an evolving galaxy. And as astronomers compare the Sun's environment with countless other stars, they begin noticing unexpected patterns that connect stellar winds, magnetic fields, cosmic rays, planetary habitability, and the possibility of life itself in ways that were once entirely unsuspected. As astronomy has matured, one lesson has appeared again and again. The universe rarely separates its mysteries into neat categories. A discovery about stars often transforms our understanding of planets. A measurement of distant galaxies influences theories about the early universe. A spacecraft studying charged particles near the edge of the solar system unexpectedly changes the way scientists think about the conditions that make life possible. The deeper researchers look, the more connections emerge. At first glance, the challenge of leaving the solar system seems to belong almost entirely to engineering. How much energy is required? How can spacecraft travel faster? What propulsion system offers the greatest efficiency? These are essential questions, yet they are only part of a much larger picture. The difficulty of leaving home is connected to the birth of stars, the chemistry of planets, the magnetic structure of galaxies, and even the evolution of life itself. One of the most striking examples involves magnetic fields. Magnetic fields are invisible. They leave no obvious trace in ordinary photographs. Yet they quietly influence nearly every environment through which a spacecraft must travel. The Sun generates a powerful magnetic field through the motion of electrically conducting plasma inside its interior. That field extends outward with the solar wind, forming the magnetic architecture of the heliosphere. Earth possesses its own magnetic field, generated by the slow circulation of molten iron within its outer core. Jupiter's magnetic field is even more immense, stretching millions of kilometers into space. The Milky Way itself contains a weak but remarkably extensive magnetic field threading through its spiral arms. These fields exist on vastly different scales, yet they are connected. Cosmic rays travel along magnetic field lines. Plasma flows respond to magnetic pressure. The shape of the heliosphere depends partly upon the magnetic field of the surrounding interstellar medium. A particle born in a distant supernova may spend millions of years wandering through the galaxy before finally encountering the Sun's magnetic bubble. The frontier that Voyager crossed is therefore not merely a boundary between two regions of space. It is the meeting point between magnetic systems operating across entirely different scales. This realization has important consequences for planets. Life on Earth benefits from several overlapping layers of protection. Our atmosphere blocks much of the Sun's harmful ultraviolet radiation. Earth's magnetic field deflects many charged particles. The heliosphere reduces part of the incoming flux of galactic cosmic rays. Each layer performs a different role, Remove one, and the environment changes. Remove several, and the surface of a planet may become far less hospitable. This does not necessarily make life impossible, but it illustrates how conditions favourable to life depend upon processes extending far beyond the planet itself. Habitability is not determined solely by the presence of liquid water. It also depends upon the behaviour of stars, magnetic fields, atmospheres, and the wider galactic environment. This broader perspective has become increasingly important as astronomers discover exoplanets. When the first planets around Sun-like stars were detected in the 1990s, attention focused primarily on their masses and orbits. Today, researchers ask much richer questions. How active is the parent star? Does the planet possess a magnetic field? Can its atmosphere survive billions of years of stellar radiation? What type of stellar wind surrounds it? Every new observation strengthens the realization that planets cannot be understood in isolation. They belong to entire stellar systems. Those systems, in turn, belong to galaxies. Connections appear even in the chemistry of life. The oxygen filling Earth's atmosphere was produced largely by living organisms, but the oxygen atoms themselves were forged inside earlier generations of stars. Carbon, nitrogen, phosphorus, calcium, iron, and countless other elements essential to biology originated in stellar interiors or supernova explosions long before the solar system formed. Every living cell therefore contains material that once drifted through interstellar space, the same interstellar medium that future spacecraft hope to cross, once carried the ingredients from which Earth itself eventually emerged. In that sense, leaving the solar system is also a return to our deepest origins. Astronomy has uncovered another unexpected relationship involving cosmic rays. For many years, these energetic particles were viewed primarily as hazards to astronauts and spacecraft. They certainly are, yet cosmic rays also contribute to the ionization of interstellar gas, influencing the chemistry of molecular clouds where new stars and planets form. Some researchers have investigated whether variations in cosmic ray intensity may subtly affect planetary atmospheres over geological timescales. Many details remain uncertain. What is clear is that these particles participate in far more processes than once imagined. A phenomenon that threatens spacecraft also helps shape the environments from which future stars arise. The universe repeatedly reveals such dual roles. Gravity gathers clouds into stars while also trapping civilizations within planetary systems. Radiation can damage living tissue while simultaneously driving chemical reactions essential to cosmic evolution. Distance isolates neighboring stars while providing the stability that allows planetary systems to survive for billions of years. The same physical laws produce both opportunity and limitation. This pattern extends to time itself. Human civilization naturally measures progress in years, decades, and centuries. Astronomy operates across much longer intervals. The Sun requires roughly 25 days to rotate near its equator. Its magnetic cycle unfolds over about 11 years. A single orbit around the Milky Way takes hundreds of millions of years. The galaxy itself evolves over billions. Against these immense clocks, human exploration has barely begun. Voyager 1 has travelled farther than any previous spacecraft. Even so, it has completed only a tiny fraction of the distance separating the Sun from its nearest stellar neighbours. This is not a sign of failure. It is a reminder of scale. Another connection emerges through observation itself. No single telescope can answer every astronomical question. Radio telescopes study cold hydrogen clouds. Infrared observatories peer through dust where stars are forming. Optical telescopes reveal planets and galaxies. X-ray and gamma-ray observatories detect the universe's most energetic events. Spacecraft measure particles directly. Computer simulations connect these observations into coherent physical models. Each technique contributes one perspective. Only together do they reveal the larger picture. The challenge of leaving the solar system has therefore become a profoundly interdisciplinary problem. Astrophysicists study stellar evolution. Plasma physicists investigate magnetic fields. Engineers design propulsion systems. Materials scientists develop radiation-resistant components. Planetary scientists explore environments throughout our own solar system. Computer scientists create increasingly autonomous spacecraft. No single discipline possesses the complete answer. Progress emerges through cooperation across many fields of knowledge. This collaborative approach has become one of the defining characteristics of modern astronomy. The universe is too complex to be understood from only one direction. Every important discovery strengthens links that previously seemed unrelated. The heliosphere, once regarded simply as the edge of the sun's influence, now connects solar physics, galactic astronomy, planetary science, astrobiology, and space exploration. A single invisible boundary has become a meeting place for many branches of science. And still, despite these remarkable connections, researchers continue encountering questions that observations alone cannot yet resolve. Every new spacecraft sends back more detailed measurements. Every new telescope reveals structures that earlier instruments could not detect. Every increase in computational power allows more sophisticated simulations of the solar system and the galaxy beyond. Instead of closing the mystery, each advance often makes it richer. The frontier continues to recede, which is why modern astronomy is now building a new generation of observatories and missions, not because the old ones were wrong, but because they have carried us to the point where entirely new questions can finally be asked. Every generation of astronomy has been shaped by new ways of seeing. Galileo's small telescope transformed points of light into worlds. Radio antennas revealed an invisible universe filled with hydrogen clouds and pulsars. Space telescopes escaped Earth's atmosphere and uncovered galaxies whose light had travelled for billions of years before reaching us. Each technological advance answered questions that had persisted for centuries. Almost immediately, it revealed deeper mysteries waiting beyond them. The search to understand the true boundary of the solar system follows this same pattern. For much of human history, astronomers could only infer what lay beyond the planets. Today, they combine spacecraft, giant observatories, sophisticated computer simulations, and increasingly precise measurements into a remarkably detailed picture of our place within the galaxy. Yet even now, the frontier remains only partially explored. One reason is obvious. The outer solar system is unimaginably distant. A spacecraft travelling for decades can sample only one narrow path through a region that surrounds the Sun in every direction. Voyager 1 and Voyager 2 have provided priceless observations, but together they represent only two trajectories through a vast three-dimensional structure. It would be like trying to understand the shape of an entire ocean by sailing along only two shipping routes. Scientists therefore rely upon many complementary techniques. Some spacecraft measure their surroundings directly. Others observe the frontier indirectly. Still others never leave Earth's neighbourhood at all, yet contribute essential information. One of the most important modern tools is the study of energetic neutral atoms. Normally, charged particles follow magnetic fields, making it difficult to determine exactly where they originated. When one of these charged particles captures an electron from a neutral atom, however, it becomes electrically neutral. Its path is no longer bent by magnetic fields. Instead, it travels in a nearly straight line through space. This simple process allows astronomers to do something remarkable. They can create maps of distant regions without ever visiting them. The Interstellar Boundary Explorer, or IBEX, has been doing exactly this since 2008. Orbiting Earth rather than the outer solar system, IBEX detects energetic neutral atoms arriving from the heliosphere's distant boundary. By recording the direction and energy of these particles, it constructs a global picture of the interaction between the solar wind and interstellar space. The mission quickly produced one of the most unexpected discoveries in heliophysics. Instead of observing a smooth distribution of particles, IBEX detected a narrow, bright arc stretching across much of the sky. Astronomers call this feature the IBEX ribbon. Its existence had not been predicted before launch. The ribbon appears closely related to the magnetic field of the local interstellar medium, but its exact formation remains an active area of research. Here, modern science offers a beautiful example of how discovery often unfolds. The spacecraft was built to answer existing questions. Instead, it uncovered a phenomenon that introduced entirely new ones. Another mission is now extending that work. NASA's Interstellar Mapping and Acceleration Probe, known as IMAP, has been designed to produce far more detailed maps of the heliosphere by observing energetic neutral atoms with greater sensitivity than IBEX. Rather than replacing earlier missions, IMAP builds directly upon them. Each generation of instruments refines the work of the previous one. This gradual accumulation of knowledge is one of the defining strengths of scientific research. Meanwhile, entirely different observatories are transforming our understanding of planetary systems throughout the galaxy. The James Webb Space Telescope has begun examining the atmospheres of exoplanets with extraordinary precision by separating starlight into its component wavelengths. Webb can identify molecules such as water vapor, carbon dioxide, methane, and other gases in distant planetary atmospheres. These observations are not directly about leaving the solar system, yet they answer an equally profound question: what kinds of environments await beyond it? Each new planetary system observed by Webb provides another comparison for understanding our own. Some stars appear calmer than the Sun. Others produce intense flares that would dramatically influence nearby planets. Some planetary systems possess giant planets orbiting extremely close to their stars. Others contain broad disks of debris resembling an expanded version of our Kuiper belt. The diversity continues to surprise astronomers. Ground-based observatories contribute in different ways. The Atacama Large Millimeter Submillimeter Array, or ALMA, studies the cold gas and dust from which stars and planets form. Its remarkably detailed images of protoplanetary disks reveal rings, gaps, and spiral structures where young planets appear to be shaping their surroundings. These observations allow astronomers to watch planetary systems developing in real time, at least on astronomical timescales. Meanwhile, the European Space Agency's Gaia mission has quietly revolutionized stellar astronomy. Gaia has measured the positions, distances, and motions of more than 1 billion stars with extraordinary precision. This immense catalogue allows scientists to reconstruct the structure of the Milky Way, trace stellar motions, identify ancient star clusters, and predict how nearby stars will move over millions of years. For any future interstellar mission, such knowledge is indispensable. One cannot plan a journey lasting decades or centuries without knowing where the destination itself is heading. Modern astronomy has also become deeply dependent upon computer simulation. Some regions of space simply cannot be recreated in laboratories. The heliosphere extends across billions of kilometers. The evolution of galaxies unfolds over billions of years. The interactions between magnetic fields, plasma, gravity, and radiation involve countless variables operating simultaneously. Supercomputers allow scientists to test physical models against real observations. If a simulation reproduces measurements from Voyager, IBEX, solar observatories, and cosmic ray detectors simultaneously, confidence in that model increases. If it fails, researchers revise the underlying assumptions. The process is iterative rather than final. Models improve continuously as new evidence arrives. This careful interaction between observation and simulation has become one of the hallmarks of 21st century astronomy. Another rapidly growing field involves the detection of gravitational waves. Observatories such as LIGO and Virgo have opened an entirely new window onto the universe by measuring tiny distortions of space-time produced by merging black holes and neutron stars. Although gravitational wave astronomy is not directly concerned with leaving the solar system, it reminds us that the cosmos contains forms of information unavailable to ordinary telescopes. Future generations of observatories may detect phenomena that today remain invisible simply because we have not yet built the appropriate instruments. History suggests that every new way of observing nature reveals something unexpected. This lesson encourages humility. Even our most advanced observatories provide only partial views. No telescope can observe every wavelength. No spacecraft can sample every location. No computer model captures every detail of reality. Each instrument illuminates one part of the puzzle. Together, they produce an increasingly coherent picture, yet never a complete one. Perhaps the most remarkable aspect of modern astronomy is how many independent lines of evidence now converge. Solar observatories monitor activity on the Sun. Spacecraft measure the solar wind. Voyager sample interstellar space. IBEX and IMAP map the heliosphere remotely. Gaia charts stellar motions. ALMA studies planetary formation. James Webb investigates distant planetary atmospheres. Ground-based cosmic ray detectors monitor energetic particles arriving at Earth. Each instrument was designed with different goals, yet their results continually reinforce one another. They reveal a solar system deeply connected to the wider galaxy, a home shaped not only by its own star, but by the environment through which that star travels. At the same time, these remarkable achievements have not eliminated uncertainty. In many respects, they have sharpened it. Modern astronomy has reached a point where scientists can identify the questions with extraordinary precision. Answering them, however, remains another matter entirely. The better we observe the frontier, the more clearly we see the limits of our present understanding. One of the quiet strengths of science is its willingness to say, with precision, "We do not yet know." To someone outside astronomy, that may sound disappointing. After all, humanity has landed spacecraft on comets, explored every major planet, photographed black holes, detected gravitational waves, and measured the faint afterglow of the Big Bang. It is natural to assume that the broad outlines of our own cosmic neighbourhood must now be completely understood. The reality is both more modest and more fascinating. The farther we have explored, the more carefully astronomers have learned to distinguish between what has been measured, what has been inferred, and what still remains uncertain. The boundary of the solar system is an excellent example. Scientists know that the heliosphere exists. They know that the solar wind expands outward from the Sun. They know that Voyager 1 and Voyager 2 crossed the heliopause into the local interstellar medium. These conclusions are supported by decades of observations, yet many important details remain unresolved. Perhaps the simplest unanswered question concerns the heliosphere's exact shape. Textbooks often illustrate it as a rounded bubble surrounding the Sun. Some early models suggested a long comet-like tail stretching behind our star as it moves through the galaxy. More recent simulations have proposed structures resembling twin lobes or a croissant-shaped magnetic configuration. Each model reproduces certain observations. None perfectly explains every measurement. The difficulty is not theoretical imagination. It is the scarcity of direct observations. Imagine trying to determine the exact shape of a mountain after walking along only two narrow trails. Voyager 1 and Voyager 2 have provided priceless measurements, but they sample only two specific directions. The heliosphere surrounds the Sun in every direction. Most of it has never been visited by a spacecraft. Astronomers therefore rely upon indirect observations and computer simulations to fill the enormous gaps. Those methods are powerful. They are also necessarily incomplete. Another uncertainty involves the local interstellar medium itself. The Sun currently travels through a relatively warm, low-density cloud of interstellar gas known as the local interstellar cloud. Astronomers have measured many of its properties, its approximate density, its temperature, its magnetic field, its direction of motion relative to the Sun. Yet even this nearby environment is not fully mapped. The cloud extends across distances far beyond the reach of direct exploration. Its boundaries remain uncertain. Its relationship with neighbouring interstellar clouds continues to be investigated. The Sun is not travelling through an unchanging galaxy. It moves from one environment into another over millions of years. How those changing surroundings influence the heliosphere remains an active area of research. Cosmic rays introduce another layer of uncertainty. Scientists understand their broad origins remarkably well. Many are accelerated by supernova remnants. Others likely arise from even more energetic astrophysical environments. Their interactions with magnetic fields have been studied for decades. Yet important questions remain. Exactly how are the highest energy cosmic rays accelerated? How do they propagate across the tangled magnetic structure of the Milky Way? Why do some observations reveal unexpected anisotropies? Small directional differences that are still not completely understood. The heliosphere complicates these questions further. It both shields and modifies incoming cosmic rays. Separating galactic effects from solar effects requires careful analysis across many years of observations. Then there is the Oort cloud. Unlike the heliosphere, the Oort cloud has never been directly observed. Its existence is strongly supported by the orbits of long-period comets. These icy visitors approach the inner solar system from every direction, suggesting an enormous spherical reservoir surrounding the Sun. Current models explain these observations remarkably well. Even so, astronomers have not yet photographed the Oort cloud itself. It remains an inferred structure. Its total mass is uncertain. Its precise extent is uncertain. Even the number of objects it contains varies significantly among different models. One reason is simple. Its members are extraordinarily faint. Tiny frozen bodies reflecting extremely weak sunlight at enormous distances are among the most difficult objects in astronomy to detect. Technology imposes its own limitations. The speed of exploration is perhaps the most obvious example. Voyager 1 has travelled for nearly half a century. Its achievement is extraordinary. Yet in astronomical terms, it has covered only a minute fraction of the distance separating the Sun from nearby stars. Human lifetimes are short compared with interstellar journeys. Entire careers may pass before a spacecraft reaches the region it was built to investigate. This forces astronomy to develop unusual strategies. Researchers design missions whose scientific return may continue long after their own careers have ended. Future generations inherit both the spacecraft and the questions they were launched to answer. Computer simulations help bridge these immense timescales. Modern supercomputers solve equations involving gravity, plasma, radiation, and magnetic fields with astonishing sophistication. But simulations possess limitations of their own. Every model begins with assumptions. Some physical processes occur on scales too small to calculate directly. Others involve interactions so complex that they must be approximated. Improving computer power reduces many of these limitations. It does not eliminate them. A simulation is never the universe itself. It is a carefully tested representation of our current understanding. This distinction is fundamental. Astronomers continuously compare simulations with observations. Agreement increases confidence. Disagreement often proves even more valuable. Unexpected observations frequently lead to improved theories. In that sense, scientific models are not monuments. They are evolving tools. Observation itself has unavoidable limits. Many astronomical phenomena unfold across timescales far longer than human history. Stars evolve over millions or billions of years. Galaxies merge across similarly immense intervals. The heliosphere changes gradually as the Sun moves through the galaxy. Astronomers observe only brief moments within these long stories. To understand the larger picture, they combine physics with observation, allowing well-tested laws to connect snapshots separated by enormous spans of time. Even then, uncertainty remains. Perhaps the greatest unknown concerns future technology. History repeatedly demonstrates that scientific instruments often transform entire fields. No one anticipated radio astronomy before radio existed. No one predicted gravitational wave astronomy before detectors became sensitive enough to measure distortions smaller than an atomic nucleus. No one expected the IBEX ribbon before IBEX launched. Future observatories may reveal aspects of interstellar space that current instruments cannot detect at all. It is therefore dangerous to mistake today's technological limits for permanent limits of knowledge. At the same time, science resists wishful thinking. It does not assume that unknown discoveries will automatically solve every problem. Some barriers may eventually yield to new technology. Others may reflect fundamental properties of nature itself. Distinguishing between the two remains one of the central challenges of modern physics. This careful balance between curiosity and restraint defines astronomy at its best. Researchers remain open to surprising possibilities. They also demand evidence before accepting extraordinary claims. Speculation inspires investigation. Observation determines which ideas survive. That discipline has carried humanity from believing the stars were fixed, lights upon a celestial sphere, to measuring planets around distant suns. It continues guiding every investigation beyond the solar system today. And yet, after all these discoveries, one remarkable truth remains. The greatest mystery is no longer hidden somewhere beyond the heliopause. It lies at the boundary between what our instruments can presently reveal and what the universe has not yet allowed us to measure. That boundary, rather than any physical edge of the solar system, has become the true frontier of modern astronomy. Every age has believed that it was standing near the edge of knowledge. The ancient astronomers who carefully mapped the motions of the planets believed they had nearly described the heavens. Centuries later, Isaac Newton's laws seem to explain the motions of both falling apples and orbiting worlds with extraordinary elegance. By the beginning of the 20th century, many physicists felt that only a few small details remained to be resolved. Then relativity transformed our understanding of space and time. Quantum mechanics revealed an invisible world governed by unfamiliar rules. The expansion of the universe, black holes, dark matter, gravitational waves, and thousands of planets around distant stars gradually reshaped humanity's picture of the cosmos. History offers a quiet reminder. Every scientific frontier eventually becomes the starting point for another. Today, the challenge of leaving the solar system occupies exactly such a frontier. We understand the basic physical principles governing spaceflight far better than any previous generation. We have measured the heliosphere. We have crossed the heliopause. We have observed planets around other stars. Yet we remain unable to send even a single spacecraft to another stellar system within a human lifetime. The contrast defines the present boundary of our knowledge. The next advances will almost certainly arrive through many different directions rather than one dramatic breakthrough. Propulsion is one of them. Chemical rockets will continue carrying spacecraft away from Earth because they will remain extraordinarily effective for escaping planetary gravity. But future exploration of the outer solar system may increasingly rely upon nuclear technologies. Several space agencies are actively investigating nuclear thermal propulsion, which could shorten travel times to Mars and perhaps the outer planets. Such engines do not promise interstellar travel. They do promise meaningful improvements within our own stellar neighborhood. Beyond that lies the long pursuit of controlled fusion on Earth. Laboratories continue attempting to sustain fusion reactions that release more energy than they consume. This goal is motivated primarily by the search for clean energy, yet its implications extend much farther. A practical fusion power source would reshape many aspects of civilization. It could also transform spacecraft propulsion by providing far greater energy than chemical fuels. No one can confidently predict when, or even whether, such engines will become practical. What matters is that the underlying physics is well understood. The uncertainty lies in engineering, not in the laws of nature. Material science represents another crucial frontier. Spacecraft traveling farther from Earth must survive decades of radiation, extreme temperature changes, and continual bombardment by energetic particles. Future vehicles moving much faster would encounter even greater challenges. Developing lighter, stronger, and more radiation-resistant materials may ultimately prove as important as building more powerful engines. The history of aviation offers a useful comparison. Progress did not come solely from stronger engines. It also required lighter structures, improved aerodynamics, better navigation, and more reliable control systems. Interstellar exploration will almost certainly demand similar advances across many disciplines simultaneously. Artificial intelligence is likely to become increasingly important. Voyager still depends upon instructions sent from Earth. Future missions traveling for decades or centuries cannot. Communication delays eventually become too long. Unexpected problems cannot always wait years for human advice. Autonomous systems capable of diagnosing faults, adapting scientific priorities, and making complex navigational decisions will become essential companions for deep space exploration. Importantly, this does not require speculative visions of conscious machines. It requires increasingly capable decision-making systems designed for environments where immediate human supervision is impossible. Astronomy itself is approaching a remarkable observational frontier. The coming decades will bring observatories far more powerful than those operating today. The Vera C. Rubin Observatory is expected to survey the entire visible sky repeatedly, detecting countless transient events and mapping billions of celestial objects. The Nancy Grace Roman Space Telescope will search for exoplanets and investigate the large-scale structure of the universe with unprecedented precision. The extremely large telescope, currently under construction, will use a mirror nearly 40 meters across to study distant galaxies and potentially analyze the atmospheres of nearby rocky exoplanets. Each instrument addresses different questions. Together, they deepen humanity's ability to understand its place in the cosmos. Future missions specifically designed to explore the heliosphere have also been proposed. Some concepts envision spacecraft traveling in directions very different from the Voyager trajectories, gradually building a true three-dimensional picture of the Sun's boundary with interstellar space. Others would carry more advanced particle detectors, plasma instruments, and magnetometers than their predecessors. Every additional path through the heliosphere reduces uncertainty. Every new measurement refines the models. Even with these improvements, certain limitations may remain. The speed of light continues to define how quickly information travels. General relativity continues describing gravity with extraordinary accuracy across every experiment yet performed. No observation has demonstrated a practical method for exceeding that cosmic speed limit. Future discoveries could certainly surprise us. Science has repeatedly encountered unexpected phenomena, but careful researchers distinguish between hope and evidence. Hope motivates exploration. Evidence determines understanding. Some of the most profound questions therefore extend beyond engineering. They concern the nature of reality itself. Why does space-time possess the properties it does? Why is the speed of light the universal limit observed throughout modern physics? Can quantum gravity eventually unify general relativity with quantum mechanics? Do unknown aspects of fundamental physics remain hidden at energies far beyond those accessible today? These questions are not asked merely because they are intellectually satisfying. Their answers could influence every future attempt to understand motion, energy, gravity, and the structure of the universe. At present, however, they remain open questions rather than established knowledge. This distinction deserves emphasis. Science advances not by replacing evidence with optimism, but by expanding evidence until better explanations become unavoidable. The history of astronomy repeatedly demonstrates this patient approach. Heliocentrism replaced geocentrism because observation supported it. General relativity refined Newtonian gravity because measurements demanded it. The existence of exoplanets shifted from speculation to accepted science because thousands were observed. The same standard applies to every future proposal for interstellar travel. Remarkable ideas are welcomed. Remarkable evidence is required. Perhaps the greatest implication of eventually leaving the solar system is philosophical rather than technological. For the first time in Earth's history, humanity would become a species whose physical presence extended beyond the environment created by its parent star. Such a journey would not merely increase the distance traveled, it would redefine the scale on which civilization thinks about itself. The oceans once connected continents. The atmosphere connected nations. Space connected planets. Interstellar space would connect stars. Yet even that achievement would not represent an ending. The Milky Way contains hundreds of billions of stars. Beyond it lie hundreds of billions of galaxies. Every horizon reach reveals another waiting beyond. The edge of knowledge has never been a fixed destination. It has always been a moving frontier, advancing quietly each time curiosity, observation, and evidence travel together. Perhaps that is why the true boundary of the solar system has become more than a scientific question. It has become a mirror reflecting the nature of discovery itself. The farther humanity travels, the more clearly it sees that every answer belongs to a larger mystery, and that realization prepares us for the final step in this journey, not towards certainty, but toward a quieter understanding of what it means to call one small corner of the universe our home at the beginning of this journey. The question seemed almost straightforward. Why can't we leave the solar system? It sounded like a problem waiting for a clever machine, a stronger engine, or a more determined generation of explorers. If the planets could be reached, perhaps the stars would simply require more patience. Along the way, that simple question quietly changed. The solar system revealed itself to be far larger than the familiar map of the planets. The sun became more than a brilliant star. It became the creator of an immense magnetic bubble that shelters our planetary family from part of the wider galaxy. Beyond that bubble lay interstellar space, not as an empty void, but as a vast ocean filled with drifting atoms, magnetic fields, cosmic rays, and the raw material from which future stars will one day emerge. Leaving home, it turned out, is not a single event. It is a gradual transition through overlapping frontiers, each defined by a different aspect of the sun's influence. The Voyager spacecraft taught us perhaps the most beautiful lesson of all. They did not arrive at a dramatic gateway. They did not cross a glowing border separating one realm from another. Instead, they measured subtle changes. The solar wind slowly faded. The particles surrounding them changed their origin. The galaxy quietly became more present than the sun. Nature had drawn no line in the darkness. Only careful observation revealed that the environment itself had transformed. That lesson extends far beyond astronomy. The universe often changes gradually rather than suddenly. Night becomes morning through countless imperceptible moments. The seasons drift from one into another. Stars are born slowly inside clouds that appear almost motionless to human eyes. Galaxies evolve across billions of years, changing so patiently that no single generation can watch the transformation unfold. The cosmos rarely announces its deepest transitions. It invites us to discover them. We also learned that the greatest barrier surrounding the solar system is not made of rock, ice, or invisible energy fields. It is made of scale. Human intuition evolved within a world measured in kilometers and lifetimes. The universe is measured in light years and millions of years. The same physical laws that allow planets to orbit peacefully around their stars also separate those stars by immense distances. The isolation that frustrates interstellar travel may be one of the reasons stable planetary systems can exist at all. The obstacle and the opportunity arise from the same geometry of the galaxy. Perhaps that is why the night sky appears both welcoming and unreachable. Every point of light invites curiosity. Every point of light also reminds us how enormous the cosmos truly is. Yet there is another way to look at this apparent limitation. Human exploration has never advanced because destinations were easy. It has advanced because understanding mattered. The first astronomers did not climb mountains to touch the stars. They watched patiently, year after year, discovering patterns hidden within familiar skies. Centuries later, those observations became mathematics. Mathematics became spacecraft. Spacecraft became the voyagers, carrying human curiosity farther than any object before them. Each generation inherited questions from the one before it. Each answered some while discovering others that had previously been invisible. There is no reason to believe the process has reached its end. Future scientists may understand the heliosphere with far greater precision. Future engineers may build propulsion systems that today exist only as careful proposals. Future observatories may reveal entirely new aspects of interstellar space that our current instruments cannot yet detect. History encourages optimism, but a particular kind of optimism. Not the certainty that every problem will quickly disappear. Rather, the confidence that careful observation, patient reasoning, and honest uncertainty gradually expand the horizon of knowledge. Science has always been strongest when it resists the temptation to confuse possibility with proof. Throughout this journey, one distinction has remained constant. Some things are measured, some are inferred, some are supported by overwhelming evidence. Some remain thoughtful hypotheses, others are simply unknown. That distinction is not a weakness. It is one of the greatest achievements of scientific thinking. Knowing where certainty ends allows curiosity to begin. The universe has rewarded that humility many times before. It may do so again. There is also a quieter perspective that emerges when considering the solar system as a whole. From Earth, our world feels immense. From the orbit of Neptune, it becomes almost invisible. From interstellar space, even the giant planets disappear into the brightness surrounding a single ordinary star. The sun itself, so dominant in our daily lives, joins hundreds of billions of similar stars drifting through the Milky Way. And the Milky Way, magnificent though it is, becomes one galaxy among countless others spread across the observable universe. Every expansion of perspective changes the meaning of home, yet it never diminishes it. Quite the opposite. Understanding how small our planetary system is often deepens appreciation for how extraordinary it remains. As far as current evidence can tell us, every human story is unfolded within this tiny region surrounding one star. Every language, every piece of music, every work of art, every scientific theory, every question ever asked about the universe, all have arisen inside the same small bubble carved into the galaxy by the quiet wind of an ordinary sun. That realization carries a certain peace. The vastness of the cosmos does not make our home insignificant. It makes it precious. It reminds us that exploration is not driven only by the desire to leave. It is also driven by the desire to understand where we began. Perhaps someday, far in the future, human-made spacecraft will routinely cross into interstellar space. Perhaps distant generations will look back toward the sun much as we now look toward familiar constellations. Perhaps another planetary system will one day become a second home. Or perhaps the physical limits imposed by nature will always keep such journeys extraordinarily rare. Today, science cannot answer that question with certainty. What it can say is simpler. The universe has not forbidden exploration. It has only asked that it proceed on nature's terms. Those terms are written into gravity, energy, space-time, radiation, and distance. They are neither hostile nor welcoming. They simply are. And perhaps that is the deepest lesson hidden within the question that began this journey. The true edge of the solar system is not merely where the solar wind fades into the interstellar medium, nor is it where the distant Oort cloud finally releases its last icy bodies to the galaxy beyond. The true edge is wherever human knowledge reaches the boundary of reliable evidence. Each time that boundary moves outward, the solar system seems a little larger, the galaxy a little richer, and the universe a little more mysterious than it appeared before. So we return, quietly, to the thought with which we began. Leaving the solar system is not simply about travelling farther than Voyager, or building engines more powerful than any yet conceived. It is about learning, step by careful step, what the universe actually is. And if every frontier we cross reveals another waiting beyond it, then perhaps the most enduring question is not whether humanity will one day leave the solar system. It is whether the universe will ever stop giving us new horizons to discover.